If you just have this puck of a certain mass sliding, presumably sliding on ice, so we can assume friction is very small. And let's use the compass directions, north, south, east, west. If this is just moving in, let's say to the east to start with, and then we give this a sudden instant kick. So we're applying a force to it, but just for one short instant in time. And of course, that doesn't mean 0 time, just for a very short amount of time. Let's say we apply a force in the upwards direction. Or sorry, northwards direction. But this force only lasts for a short time. And what would you expect to happen to the puck in that case? Just intuitively, what would you expect to happen? If the puck is already going this way and you apply a kick to the north, what would you expect to happen to it?
It's going to move northeast.
Yeah, it's going to start moving to the northeast. Maybe not exactly 45 degrees northeast, but somewhere in the northeast-ish direction. And also after the kick, what sort of path would you expect it to follow? As it moves northeast-ish, what sort of shape would its path be?
Straight.
Yeah. Should be moving in a straight line. Because the only way the path can curve is if there's a force acting on it right now. If you've got an object moving on a curved path, if you take a look at the object's velocity, like at this instant in time, and then the object's velocity at this instant in time, the velocity is now in a different direction. Even if it's the exact same speed, moving at the same rate, it's now traveling in a different direction. And then at this later instant in time, it's now traveling in a different direction as well. In general, if an object is moving on a curved path, its velocity is changing all the time because it's changing which direction it's traveling all the time. And the only way you can change the velocity is by applying a force. So the only way for an object to be moving on a curved path, even if it's moving at constant speed, is for it to be experiencing a force all the time. If there's no force acting on it, it can only move in a straight line at constant speed, or it could be staying still. But this goes back to Newton's first law, that the acceleration is 0 if the sum of the forces is 0. And that actually goes in both directions. In mathematics, we often write that as IFF, which is short for if and only if. It just means the if then goes in both directions. If the acceleration is 0, then the total force is 0. And also, if the total force is 0, then the acceleration is known to be 0. So that would be covering an object that's not accelerating. Either it's staying still or it's moving in a straight line at constant speed. The only way for it to be accelerating is for it to be experiencing a force. And this is usually referred to as Newton's second law, that the sum of the forces acting on the object equals its mass times its acceleration. Changing velocity as time passes counts as acceleration. So this curved path requires a force acting on the object. And by the way, if the object is moving in a curved path, which direction would you expect the force to be on that object in order to make it move in that curved path?
Towards the center?
Yeah. If you think of this path as a portion of a circle with a center somewhere, if you've got an object moving at constant speed on a curved path, specifically a circular path, the force that makes it curve has to be a force towards the center of that circular path. which also means that force is going to be perpendicular to the velocity vector itself. A force perpendicular to the velocity vector causes the direction to change, but it doesn't exactly cause the speed to change. Because to change the speed, you've got to apply a force. Like, let's say you want the object to go faster. Which direction would you want the force to be in? If you just got an object that's already in motion and you want it to go faster, which direction would you apply a force?
Horizontally?
Well, in this case, yeah. More generally, whatever direction it's already moving. So you apply a force in the direction it's already moving, it gets faster. What if you apply a force exactly opposite to that direction?
Slower.
Right, and it gets slower. Maybe even come to a stop and reverse direction if you apply the force long enough. So any force parallel to the velocity only changes the speed. Apply a force with the velocity, you make it go faster. Apply a force directly against the velocity, you make it go slower. If you apply a perpendicular force, though, perpendicular is not with or against. It's a different dimension entirely. So a perpendicular force, a force perpendicular to the velocity, doesn't change how fast the object is going. It changes the direction of travel. On the other hand, if you've got a force along some diagonal, let's say you've got an object that's traveling, let's say, directly to the east right now. So its initial velocity is to the east. If you apply a force, let's say, to the northeast, what would you expect that force to do to the object's motion?
They're kind of compounded, so like some energy is lost, I guess, or maybe energy is not the right word, but like some's lost, but it's changing direction.
It is going to do some of both, yeah. And I wouldn't necessarily use the term energy here because it is going to be gaining kinetic energy in the sense that it's going faster. But this force is going to partly make it go faster and partly change the direction. It's not purely in the same direction as the velocity. So it's not only going to change the speed. It's not purely perpendicular, so it's not only going to change the direction. It's some of both. And you can think of this by splitting it into components. Not necessarily X and Y components in the usual sense, but a component in the direction of the velocity and a component perpendicular to the direction of the velocity. The parallel component of the force changes the speed. The perpendicular component of the force changes the direction of travel. So both components are changing the velocity. We can just split it up into the part of the force that changes how fast the object is moving versus the part of the force that changes which direction the object is traveling. And we usually call those, instead of calling it the X component and Y component, we would usually call it the parallel component and the perpendicular component. So we would call that the component in the same direction as the velocity, we would call F parallel, usually written as F with a subscript parallel sign. And then the other component we would call F perpendicular, or F perp. And F with a perpendicular sign is the subscript. So the parallel component is the part of the force that changes how fast the object is moving. The perpendicular component is the part of the force that changes the direction of travel. Any questions on that so far? So in this case, we have a force that's entirely perpendicular to the velocity. So what is that going to change?
Is it the direction?
Yeah, that'll change the direction. It won't change the speed, and it will only happens for this one instant. So we've got just this very small change to the direction. It's going to be changing from moving this way to suddenly moving this way instead. And note that it's not going to be suddenly moving straight up because the force we apply causes a change to the velocity we already have. If you have the existing velocity, and you can even write this as a momentum chart, might not be the most efficient way to do it, but it's certainly a way to organize the information. If you think of this in terms of initial momentum, change in momentum, and final momentum, Of course, there's only one object here, so we don't need multiple rows and a total row. It's just the puck and that's it. The initial momentum is mass times the initial to the right or to the east. And then we've got a small change equal to this amount of force times how much time it lasts. So the change in momentum in this case is not 0 because we do have an external force. That change is going to be this amount of force times how much time it lasts. Presumably a small amount of time, so this is going to be a small change in momentum. But how do you find final momentum then?
Could you do PI plus delta P equals PF and then add them?
Yeah, all we need to do is add these together. The initial momentum plus the change in momentum equals the final momentum. And since we've got these as drawings rather than as specific numbers or components or anything like that, I would just draw that on an XY plane using the head to tail method of addition. That we have our initial momentum looks like this. And then we're going to add delta P. So we do this head to tail. We go initial momentum, and then from there we follow delta momentum. And then the total moment, the final momentum is going to be just the straight line vector from start to finish. So P final is going to be this way. The final momentum, the thing is, this isn't always a right triangle. It's not even necessarily a triangle. In general, if you're adding vectors, like let's say we were adding 3 vectors together. If you wanted to add this vector plus this vector plus this vector, the way you would draw that, if you wanted to use the geometric approach, you got this vector plus this vector, and that means you follow this direction for this far, starting from where you left off. So we're basically treating the end of the previous vector as the new starting point. I usually think of this as imagining you're following directions to get somewhere. Like this vector says go this far to the north, and we've done that. Then this vector says go this far to the east, so we're going to do that from where we just left off. And then this final vector says from where you just left off, go this far to the north-northwest. So you're just following this set of directions from your original starting point, but then you keep going. And the total, the sum of these 3 vectors, is just the straight line vector from the original starting point to the final ending point. So this would be the sum of those vectors, whatever vectors they happen to be, not necessarily momentum, but any vectors we could be adding together, from the original starting point to the final ending point. Because the sum of vectors is basically telling you the one vector that has the same effect as all of those put together. So in this case, it does happen to be the hypotenuse because we're adding 2 vectors at right angles to each other. But the vectors we're adding together don't have to be at right angles, and it doesn't have to be just 2. We might be adding multiple vectors together. Any questions on that so far? So it looks like the path this is going to take then is it's going to go in, it's going to go to the east for a while. And then at the instant where the force is applied, it suddenly changes direction. And it's now traveling in this direction. And before the kick, it's traveling in a straight line. After the kick, it's also traveling in a straight line, just in a new direction. Any questions on that so far? And I think some of this was a multiple choice question, if I remember correctly. Some of the questions involve, some of the options involve like going straight up or straight to the north. Why isn't this just going straight to the north after it experiences a force to the north? Or what would you have to do differently in order to make it just go straight to the north?
Wouldn't the puck have to be like stopped and then kick it for it to go straight up?
Yeah, you'd have to stop its eastward motion and then give it some northward motion. In this case, we're giving it some northward motion, but it still has the eastward motion it already had. In fact, you could split up the final momentum into components as well. You've got the eastward motion it already had, plus the new northward motion that you added in. So if you want it to go straight to the north instead, you need to bring its eastward motion to a stop and give it northward motion as well. And you can do that all in one kick. It's just that the kick would have to be in which direction? How would you, which direction would you kick it to simultaneously stop its eastward motion and give it some northward motion?
Would it have to be at like, okay, I don't know if this is right, but like 135 degrees or something, where it's like, it's back in the same direction.
Like that?
Yeah, yeah.
Yeah, that should work. And maybe not exactly 135, but somewhere in that quadrant, depending on how strong the kick is and how fast we want it to be going to the north afterwards. But yeah, if we apply a diagonal kick to the west and to the north, the westward component of the force brings the eastward momentum to a stop, and the northward component of that force creates some northward momentum. So we can do both at once by using that diagonal force. If we apply a force for some amount of time to the northwest, as long as the change in momentum has a westward component that exactly cancels out this eastward value, and it also has a northward component, when you add those together, the eastward component and westward component cancel out, so all that's left is northwards. Of course, that's going to have to be done in a very precise way. You'd have to be applying a very specific amount of impulse in order to precisely cancel out the eastward component of the original momentum. But it's certainly possible. You can change whatever the starting momentum is to whatever other momentum you want. You just need to apply exactly the right impulse. And you can always find that impulse by subtracting to find the difference. If you have, like, let's say we didn't already know the change in momentum. If we know the initial momentum it has, and we know the final momentum we want, we can just subtract final minus initial to find the change in momentum that's necessary to make that happen. And that change in momentum at least tells you the direction the force needs to be, and the amount of force times time. Any other questions on that? All right, then let's take a look at this circuit problem you sent me also. Get some review on that. And then if we have time after that, we can get into rotational motion as well. Let me pull this up on share screen. So here's this circuit we've got. And what are we trying to find here?
It's the change in voltage across R1.
Yeah, so to find that change in voltage, we know the resistances, right? Or I guess R1 is unknown. So we don't know R1, but we do know some other things. We know all the other resistances, and we know the current through the battery. So I would start by labeling all of those. We know current through the battery is 6 amps. And what other currents do we need to consider here? We call this maybe IO. What happens to the current when it hits this junction?
It diverges or splits.
Yeah, that's going to split into two paths. And one of them is going to be going through R4 and R5 and then joining back up. So let's call that, since we don't know what that current is, let's call that unknown current, let's say I4, since it's the current through resistor 4. And also the current through resistor 5, but we just need one label for it. And the other current, what's going to immediately happen to the current going down here?
It splits again.
Right, that's going to split again into, let's say, R1 and R2. Or let's say current one, I1 and I2. So I1 is unknown, and also I2 is unknown. But then those merge back together to form a new current, let's say I3, which is also unknown. So it looks like we've got 5 different currents here. We got I1, I2, I3, I4, all unknown. And I0, the current through the battery, we do know, 6 amps. So we're going to have to figure out what some of these currents are. And we know most of the resistances. Let's label the resistances we've got. You know, R4 is 3 ohms. And we know R5 is 9 ohms. We also know R1, no, we don't know R1. We know R2 is 6 ohms and R3 is 2 ohms. So that labels all the resistances. And the problem is, since R1 is unknown, this entire region is going to be difficult to deal with. But we do know something else. We know since we know R5 and R4, and also how are R5 and R4 connected to each other?
In series?
Yeah, those are in series. So what should we be able to do? What should we be able to do with the resistors if they're in series?
Can add them.
Exactly, we can just add those together to find the total resistance of that entire region. So if we just add those, we can say this entire region acts like just one big 12 ohm resistor. So this just acts like ohms. So I'm just going to call that R45. The equivalent resistance of resistors 4 and 5 together. Also, we know what's the voltage drop for that entire region. How much voltage is that path getting?
It's 18?
Yeah, that path is getting the full 18 volts of the battery. Because if you look at this entire upper path and this entire lower path, those paths are connected in parallel. even though the individual paths involve splitting up into more complicated situations, if you look at just the upper path and just the lower path, those branches overall are in parallel. You can also see this from labeling voltages, that if we label, let's say we label the voltage before the battery 0 volts. So let's say we call this region 0 volts. Then not only that location, but this entire region, again, as usual, we can keep going until we hit an actual something other than wire. This entire sort of E-shaped region over here is all a 0 volt region. So that's all at 0 volts. And then the battery just adds 18 volts, the plus epsilon from the battery, which means that the location after the battery, and in fact, this entire region is all at higher voltage, specifically positive 18 volts. And again, we can keep that voltage going until we hit something other than just wire. So this entire region is all an 18 volt region. So even if we don't know what's happening in between, we know that this overall upper path goes from 18 volts to 0 volts. So it's got a delta V of negative 18 volts. And we know its resistance. If we know voltage and resistance, what can we do?
Find current.
Yeah, we can find the current. Using the usual delta V resistor equals negative IR, Ohm's law, then the current is going to be delta V negative delta V over R. We know the voltage drop here is negative 18 volts. It's losing 18 volts from start to finish of that entire path. So negative 18 divided by the total resistance of that path, 12 ohms, is 1.5 amps. So that's going to be the current through resistors 4 and 5 together. Current 4 is 1.5 amps, we now know. Any questions on that path so far?
None for me.
And now that we know current 4 is 1.5 amps, what else can we immediately figure out about current? What other current can we figure out based on the currents we now know?
Is it like current through the whole like I3? Is that right?
Yeah, we should be able to figure out I3 because if we take a look at the currents leading into that, we know, for instance, that at this left junction, we can see the current flowing in and the current flowing out. So if you consider this junction, there. At this junction, we've got current flowing in and current flowing out. What currents are flowing in versus what currents are flowing out? That is, which labels are on the currents flowing into that location?
I3 and then the I4, 5, or I4, I guess we call it.
Yeah, we know we've got I3 flowing into that point from below, I4 flowing into that point from above. So I in is just I3 plus I4. What currents are flowing out of that location?
Is it considered I naught or no?
Yeah, I naught is flowing out of that location because remember, I naught is flowing through this entire central wire. Every point in that central wire has that 6 amp current. And that is definitely flowing out of that junction. So we can say I3 plus I4 equals I naught. You can also do this on the other junction as well. This junction here, we've got I0 flowing in, and flowing out, we've got I4, and we didn't really label it, but this corner is also technically I3. Because this current splits up into I1 and I2, but we know I1 and I2 join back up to I3. So that means over on this lower right corner, the current is also just another copy of I3. Either way, we find that I3 plus I4 equals I0 from the junction rule, and we can fill in some of those values. We know that I4 is 1.5 amps. We know that I0 is 6 amps. So what does I3 have to be?
4.5 amps.
Yeah, exactly. Subtract the 1.5 amps from both sides, you get 4.5 amps. So that is the current through branch 3. We now know that current. So we can fill that in. Any questions on the current so far? And it looks like we're still missing current 1 and current 2. And the fact that we, sorry,
I had a question. So I mean, maybe I guess my intuition's, or it is wrong, but I0 is after it's gone through the 8-volt battery. So how can we say that before it's 6 amps and after? Before the battery and after the battery it's 6 amps.
You can think of this as another application of the junction rule, that if you consider if you just draw a box around the battery, the current flowing into that box has to match the current flowing out of that box. The battery doesn't really create current. The battery pulls the current through. I find it might be very useful to think of this as being like a bicycle chain. Like if you turn the pedals on a bicycle, you're pulling chain through. You're not creating chain. The chain just doesn't come out of nowhere and leave the pedals. When you turn the gear on the pedals, you're pulling chain through the entire cycle. You're making the entire chain move. For the battery and current, it's very similar. The battery isn't creating charge out of nowhere. The charges are already there. The wire already contains all the electrons it ever needs. The battery is just pulling the electrons through. And that includes electrons leaving one side and electrons entering the other side. So you're causing motion in the electrons that are already there throughout the entire wire. Does that make more sense?
Yeah, I think so. Thank you.
So and also just from the continuity principle, we should expect the same current on this entire wire because it's only one path. Any other questions on current so far? So we now know the current everywhere except how it splits up into R1 and R2. And that's going to be trickier because we don't have a value for R1 yet. So we can't just say like, oh, more of it's going to go this way and less of it's going to go this way. We don't even know whether R2 is the weakest or strongest resistor in this network. But we do know now the current in R3, and we know the resistance in R3. So if you know current and resistance, what do you get when you multiply those?
The voltage drop?
Yeah, exactly. We can find the delta voltage for resistor 3 by just multiplying those. 4.5 times 2 is negative, of course, because it's a voltage drop, negative 9 volts. So that means as we pass through resistor 3, we lose 9 volts. If you lose 9 volts and end up at this blue 0 volt region, what did you have to start at in order to end up at 0?
9.
Yeah, so that means we can say that this in-between region, right before resistor 3, this region is a 9 volt region. And we now know the voltage everywhere. We've labeled, well, except between resistors 4 and 5, of course. We could figure that out, but we don't really need it in order to proceed from here. Because R4 and R5 can basically just be treated as one big resistor anyway. But we now know the resistance or the voltage in this in-between region. And that means R2 is getting how much voltage? What's the voltage on one side of R2 versus on the other side of R2?
Wait, so, oh, because the 18 has to go through, is that right? So then it's 8.
Yeah, well, I don't know if I'd say go through. It's more that this entire pink region is all 18 volts, including this point right here. And this entire green zone in between is all 9 volts, including this point right here. So resistor 2 is a bridge from an 18 volt region to a 9 volt region. So what's the delta voltage there?
-9.
Right. Resistor 2 is also getting -9 volts of delta V. Which means for resistor 2, we now have voltage and resistance, so we could find current. But more importantly, how are resistors 1 and 2 connected?
Parallel.
And what do you know about voltage of resistors arranged in parallel?
I believe they're equal.
Right, which means we now know the voltage across resistor 1. Resistor 2 is getting -9 volts, so resistor 1 is also getting the same -9 volts because they're in parallel with each other.
So you actually never had to solve for current of R1 to find the voltage then?
Right, if all we care about is the change in voltage, we just found that just by looking at the other voltages elsewhere in the system. We could also now figure out current by taking voltage divided by resistance. So that should be 9/6 is 1.5. So we could continue filling this in. We now know I2 is 1.5 amps from delta V over R. And since we know I2 and I1 have to combine to get 4.5 amps from the junction rule again, we can say I1 is whatever's left. 4.5 amps minus 1.5 amps is 3 amps. So we know current 1 is 3 amps. And we know the delta V is 9 volts. So you could multiply or divide those as well. 9 volts over 3 amps is 3 ohms. So R1 has to be a 3 ohm resistor. Any other questions on that?
Yeah, so just one question. When I tried to do this problem on the midterm, I tried to think of it as in like, I don't remember what we called it, but where you like reduce I figured that like if we knew, I was trying to use the epsilon equals IR because
like
we know.
To a single equivalent resistor?
Yeah, so why wouldn't that have, because I figured like if we only, R1's the only unknown because you know epsilon and then you know I is 6. So
yeah, I think that should work. If you reduce there's an unknown resistor, but if you find the equivalent resistance as some formula in terms of R1, and then you can say 18 volts equals 6 amps times that formula, then you'll have an equation where R1 is the only unknown. So that's certainly possible. It just might be algebraically more complicated. But it does lump everything together into one step, and that's often useful too.
Okay, but then I guess like that's not what the question's asking, so it probably overcomplicates it.
Well, no, I mean, that would certainly be a possibility. You could use that to find the resistance in R1. I guess it would take more steps because you'd have to find the resistance in R1 by solving that formula and then analyze all the currents and then figure out the voltage drop. So I think because this is asking about voltage, it is going to be faster to work in terms of voltage to begin with.
And then last question. So for this one, it's not as much about formulas and math as it is just like understanding like the different rules associated with current and like manipulating.
Yeah, and of course there is formulas and math involved as well. We needed that to figure out the individual changes in voltage and the individual currents. But I think more important than that here, I mean, the formula in the real world, formulas you can just look up when you need them, or with enough practice, they just become second nature anyway. But the really important thing here is understanding how that all fits together and being able to look at a circuit like this and think, well, I know this and I know this and I don't know this, but I can figure that out if I know this other thing. So how can I find that other thing? And it becomes very logic puzzly, being able to look at all these different parts and look and ask yourself, how do these fit together? If I'm missing this one, how can I find it if I have these other ones? So understanding conceptually how all these fit together, I think, is probably far more important than any one formula.
Yeah, thank you for doing that.
Mm-hmm. Any other questions on the electrical circuit stuff? All right, looks like we are out of time for now, but if you want to get a start on the rotational stuff, I think a big part of the problem with the rotational stuff is that it introduces a whole bunch of new terminology that can be very confusing at first. But all of that terminology, or almost all of it anyway, corresponds to terminology we've already seen for translational motion. And I put together a chart that just describes how those are all related. Let me put a link to that in the chat here. If you go to so math.nchoose.org/P7B and click on the link that says Kinematics Chart. It's got a couple of charts listing out all the important terms for translational motion and all the important terms for rotational motion, their units of measurement, their definitions, and how they're related to each other. So take a look over that, familiarize yourself with the terms for rotational motion and what they actually mean. And we'll take a look at how those all interact together next time. See you then.
Thank you.
You're welcome.
Thank you.